sit back and relax. Yeah. So I think the general idea for what I'm going to be talking about in this workshop is right now, I'm just going to give a little bit of background right now, some general considerations that we need to start thinking about when analyzing data, and then tomorrow after Marquito gives his talk, I'll work through some exercises so you'll be able to run some of the same code and plugins over actual data. So the main point of this talk is basically that most of what you've heard so far is a lie, to a certain extent, right? So, and so you can kind of think of what's going on. It's kind of like getting a cake, right? Maybe you sit down and you come up with an idea of what your perfect cake looks like. It's really awesome, and you send your order to the cake shop, and then you get back something with some extra features, right? So, maybe in 3-5 years, something like that, when you do an analysis with simulation, then it'll correspond very well to data, and everything will look nice. But right now, you want to tread carefully, and when you're making cuts, like the cuts that we've been talking about, it's good to use simulation as a guide, but you should keep them loose and then be careful when you look at data. So I'll be showing some comparisons between simulation data here, and we'll see how well they agree. So when you're talking about these sorts of comparisons, there's lots of issues that you can kind of talk about, which even go into the ideas of, how do you design a measurement, how do you deal with efficiencies and backgrounds and blind analyses and all these other things. And so you could talk for a day. And so I'll only cover a few of them right now and, at least give you a little bit of food for thought. So, we can start. So one thing that, of course, we need to think about is backgrounds, which we've talked a little bit about before. And, of course, there are different data in simulation. One of the nice things about this 3-pi mode is that it looks actually pretty good. So here's a simulation. This is based on some of the files that you guys have been working with. The cuts are a little bit more loose. But you have the same thing, right? You have this huge omega peak. You see some signals from the eta and the phi if you look farther out. And then I ran the same code just over a small bit of the data. Right now, this is a latest data production run, and so you see some of the same general features. You still see 3 bumps, but the background, the statistics aren't great, but it seems like, well, okay, maybe it's a slightly different shape. So, maybe when you project it down here underneath your omega peak, different fractions of the data. And then also you can see that the resolution clearly is not as good, right? This peak in simulation is larger than it is here. This is probably the phi, but it's a little bit more washed out. And so, it's good that you see these things, but when you're actually, analyzing your data and deriving results from this, you need to make sure that you take these things into account. Again, this background, so this is actually a mixed simulation. So the omega comes from the detailed amplitudes generation that has all the right angular variations taken into account. This background is all from the Sim1 measurement. And so, the first thing that you have to be really careful about is that, you really need to be careful about making predictions on your background based on these simulations, right? This Pythia is only as good as how well you've tuned it. There's a lot of parameters. And so generally what one can say is that it's maybe okay at this point for inclusive properties, the general properties of the event, but exclusive reactions need to be carefully looked at on a case-by-case basis. And this has been shown by other people before. So when you're actually looking at data, you kind of want to determine backgrounds actually from the data where possible. And so you can do this by using various ideas, like a data-driven feed-through estimation, where you do some sort of detailed Monte Carlo simulation. You get a background, and then you can normalize that somehow based on some other measurement of that data. An easy way is, of course, looking at sidebands. So here, I just took kind of a loose cut of all these events. This is the missing mass squared of the 3 pi, which, as you expect, peaks around 0. And so, we're not cutting on this variable, but when you do a kinematic fit, you're going to be selecting events from here. So if you look at the sidebands in these regions, then these are from poorly measured events or something like that. And then you do the rest of the cuts. Yeah, it's a little difficult to see. I was just generating this plot right before the meeting, but here you can see that after this simple kinematic fit selection, this small bump of events comes from these regions of the data. So this is one way of controlling what your backgrounds are. A really nice example of this was we saw yesterday from Jane's talk, right? Besides backgrounds due to event selections, backgrounds going in under there, we also have these backgrounds from the beam. If you're looking at exclusive reaction, you don't have just these prompt photons that are the correct ones for your reaction. You also pick up accidentals or randoms, whatever you want to call them as well. So one thing that you can see here, right, is that if you're studying this thing in Monte Carlo, your incidental level is only as good as your simulation in NC smear, and clearly there's a difference. Right now these levels agree on the order of 50%, but well, you at least hope that if you properly subtract the Monte Carlo, properly subtract the data, hopefully that will be fine. But this is another thing to be careful about. But at least as she showed, the idea here is that to subtract these out, you look at the events that lie in these bins, properly normalize them to the data, and that's what you get here. This is the total number of events. These are the random ones subtracted out. And so, again, this is something that you have to deal with using data rather than simulation. So, we're starting out measuring some simple things like asymmetries and other things that are a little bit more simple. There you can get those pretty well through data. If we wanted to do something like cross sections, so just to remind people, the number of events that we see in the data is the cross section times the total luminosity. This is the probability that the reaction happens multiplied by the amount of data that we have. So we write it like this. Then we can kind of solve this for the inverse. So this is what we measure. We get efficiencies by looking at data in Monte Carlo, and this is measured some other way. So this is clearly easy, right? It's just 3 numbers. So that's of course before you go into all the caveats, right? You don't, when we measure something, you don't just have this. This is really the number of signal events. It's the number of measured events minus the background. Efficiency, is always really difficult. You need to make sure that you get this right. And there's a lot of pitfalls that one can get into calculating this. So we can talk a little bit about that. And then, you also need to make sure that you're correctly measuring the amount of data that you have, right? And so this depends, and on our experiment, depends on getting the photon flux correct. You need to know your target density correctly. You need to know your lag times and things. And so I'll talk a little bit about some of the considerations that are going to go into measuring these quantities here. So, so the acceptance, so this is a probability that the particles actually make it into your detector. So, you can sort of factorize your overall experimental efficiency into acceptance, into this acceptance, and then the probability that you actually reconstruct things. So there's a couple different ways that you can look at this. If you're looking at simulation, there it's really easy because you know all the particles that you generated, and you can see where they go into the detector. You can look at, if you just generate it without any dynamics, so it's just flat angular distributions everywhere. You can look at how the reconstructed angular distributions go, or you can look at the Dalitz plot. So this is the real Dalitz plot, n squared of one charged pi 0, and the other charged pi 0, and so the events should be more or less even over here. This is the thrown level, but then you can look at the reconstructed distributions, and then see if it's still even over this Dalitz plot, or if there's some other problem. So of course you can't do something this easy when you're looking at data, right? Unfortunately we don't know all the distributions of the generated particles, but you can at least look at some other simpler reactions that don't, that should at least have some sort of even distribution over the whole detector. So one thing that you can look at this in some simple reactions that are really well known, or don't have complicated dynamics, or you can look at generally some features of data that were taken with this amorphous radiator. So we've been talking a lot about that's when we're measuring things like these spin density matrix elements and stuff like that. There we have a diamond radiator to create this partially polarized beam. But if you just put in, we have some of these amorphous radiators. They're just pieces of aluminum, and so those just have a much simpler spectrum and none of these polarized effects. And so you can do things. You can do some really simple things like here, if you look in data, this is just the total number of reconstructed tracks of different types, 2 different pions and protons, as a function of phi and theta. And so, you can see generally it's in all these distributions, and this happens consistently in our data right now, that but so sorry, it's a little more obvious with protons, that there's some sort of phi modulation, right? Right around in this part of the detector. The efficiency is a little bit higher, lower here. It's a little bit higher here. And so this is, for paying attention. This run isn't in the range where we had some problems with the CDC. So this is kind of an issue that we've seen consistently in our data so far, which we need to understand. But when you're actually looking at calculating your efficiencies, you need to properly take into account these effects. So then you also want to look at the efficiency of your reconstruction. There's a lot of different ways that you can do this, but if you know what reaction that you're looking at, the simplest way is to if you know, so for example, in this omega final state, right? If you want to know what the probability, for example, that the pi 0 is reconstructed, what you can do is that you can reconstruct all the other particles and then make a kinematic fit where you're constraint in the kinematic fit is that you're looking for the missing mass of that event, and then selecting events that have a missing mass around the pi 0. So then you have some sort of tagged events, and then you can actually look in your data and see how likely it is that the pi 0 is reconstructed, and then get your efficiency in that way. So, Paul's done some analysis, and so there's a lot of caveats to be given about these plots, right? There are backgrounds that still need to be understood and subtracted away, and a lot of other effects. But one can at least compare data and simulation, and and look at the ratio of these, and at least get a broad feeling for how the efficiency varies, in the detector. And you can really see some general features of it, right? So, the analysis that he'd been doing was just looking at these pi plus pi minus proton events, and looking to see how well things are reconstructed. And so, at least already in here, you can see that so this for pi pluses, and here particles are reconstructed reasonably well in the central part of the detector and in the front part of the detector, and then you see this dip region in here, right? And so this is the area. We have a central tracking detector, we have some forward tracking detectors, and then there's a transition region where the tracks are, either hitting both of them or maybe, hitting some of them and then missing the forward one. And so, you can see here that you have this sort of inefficiency. And you can look at the ratio between these two things where, the Monte Carlo is looking a little bit better in the forward region, and it's different here. And
well, I would say at the forward angles, the efficiencies are roughly matching because the difference is 0.
Oh, sorry, yeah.
But the backward angles, it's not. However, caveat laden, there's a lot of background, and the background's different for data in Monte Carlo. All the pions are going forwards. So I wouldn't take the result necessarily for its word. They might match at backward angles, but the procedure itself is the idea that you need to do these kinds of comparisons.
Right. Yeah. So it's like, well, it's also that you need to do these types of comparisons and use this sort of information to get out efficiency correction. And then you also have to be careful, when you look in simulation data, and especially in these gaps in the detector, right? Because the efficiencies in these regions will depend on making sure that the tracking is working correctly, that you have the right efficiencies. And so the amounts of the dips can be different in there. And, if you're doing an angular analysis, right, that can introduce different features and different problems. So,
and if there's like an area like at the bottom left corner where you just can't get data in Monte Carlo to match up, you're better off. You're basically saying that my simulation can't model the real experiment there. I better just cut these away on my analysis. So if you don't want to do that, you want to fix things. But at the end of the day, if that's still there, you need to cut it.
And so, of course, you want to do these for all the different particles. You can look at chart at pi pluses, pi minuses. Protons, again, they look very different, but the general idea of all this thing is the same. And one thing to keep in mind in here is the fact that these acceptances and efficiencies are reaction dependent, right? You can see that in this reaction, the pions and the protons illuminate different parts of the detector, different angular regions, different momentum regions. And so, eventually we'll have some sort of standard numbers and things like that that'll at least give you a basis from where to start. But, when you're doing your analysis, you really need to go through and evaluate all these numbers yourself. And then resolutions. So resolutions are another issue that you need to take into account. These will feed into a lot of different things, right? So it will affect the different cuts that you make in data, whether it's on these delta t distributions. They'll affect your chi-squared results from your kinematic fits. And they can come up in really obvious or more subtle ways. So to give you an example, this is something that I showed yesterday, where this is the time resolution on the start counter. And so you can see that it's different in data, where it's about 270 picoseconds, and in Monte Carlo it's about 350 or 370 picoseconds, depending on the conditions. And so, of course, you're not going to cut directly on these numbers, but these are the numbers that get propagated into the calculations of delta t, or if you're cutting on beta versus p, and then, or if you're using like a figure of merit cut, right? And so, these are the sorts of numbers you have to be careful about. And when you're making some of the cuts that Justin was showing, when you're looking at data, don't just trust those. Look at those distributions. And this is an example of something that came up in the discussion of what Justin was showing, that the resolutions and the values of some of these things right now can change between runs. So this is the ddx in the CDC as a function of momentum. And this red line, you can call it, like, you could use it as a cutter, but it at least guides your eye right now to see. So this is the BG Gen Monte Carlo, and you can see this. This is the main pion band, and then here, I don't know, can you see this proton band right here? Okay. And so this is what it looks like in Monte Carlo, and if you're developing your analysis, you say, okay, well, I'll cut on this, and then that'll be fine. But then if you look at this various run, it's clear that for this particular run, the band is in a similar location. It's a little wider, so you think you may, okay, I'll make a slightly looser cut. But when you look at these different ones, this band is shifting slowly farther down. And so, these numbers are just not calibrated terribly well at the moment. And so, you want to be careful, and so this is one of those times where you want to look at the values that you're cutting on, because if you're making a cut based on this, or even based on this one particular run, then you're going to start cutting out a lot of events in these other runs. Right, yeah, and so here's kind of a projection of those things, and so you can really, and that really gives you a feeling for how this peak is shifting around. So, of course, this is the sort of thing that can be calibrated away and will be, but may not be fixed for the first production run. Again, and so, yeah, so aside from those values, of course, you can look at the resolution for track reconstruction. This will feed into your chi-square values and things like that. And so, what you can at least compare data in Monte Carlo a little bit, and you can see it's what is this? This is the this is the momentum resolution, right?
Yeah.
And so the data in the Monte Carlo for protons, at least, it's similar within data, or sorry, within errors. But there's maybe some shifts. Certainly, there are different features, and there are a lot of the same caveats that Paul was giving before, but it's something that you need to look at. And so, yeah, again, this is the angular distribution, or the angular resolution, at least in terms of theta. And so, I think that the point that I want to make here is that you can see that it's okay out here, but when you go to lower the lower momenta, there's a large difference here. And so
the y-axis is different.
It's not so different.
The y-axis is different.
No, you're right. The y-axis is different.
That's why I sent you a new plot.
Okay.
It's not so bad.
Yeah. No, you're right. It's not so bad. I'm sorry. It was late and I showed the wrong plot. Okay. Well, then that's good to see. I mean, you don't have to worry about that. Yeah.
10 minutes.
Okay. So those are some things to keep in mind. So then, let me also talk about some other things that go into these calculations in terms of the photon beam. So we need to measure the amount of data that we've actually been taking, right? So that depends on us knowing the photon flux. And so when you want to figure out the amount of data that you have, you want to measure this amount of data using some sort of well-understood QED process, or some well-understood process. Usually this means QED. And so what we mostly do is looking at, so it's the photon pair production in the electric field of some nucleus. And so so if we're kind of looking into the experimental hall, the main GlueX detector kind of sits down here, and so then upstream, if we have the photon beam coming here from the from the Tiger Hall, then the way that we measure it is that there's some converter here in the beam line. The photons get converted to E plus E minus pairs. They go through this magnet that bends them, and then goes into these counters. And so the idea is that, just briefly, we have, here's an example event where you have an electron and the positron, and then what you look for is the matching of two hits that are in time, and then these coarse counters, and then use these fine counters to actually measure the energy. And so this gives us the ability to look for the photon flux for energies, for photon energies from 7 to 12 GeV. And so just to give you an example of what this looks like, this is sort of the raw photon flux for one event. And then the distribution, the acceptance of this detector is a little bit triangular, right? So if you do the full analysis and correct it for the acceptance, you get this distribution, which corresponds to the post-collimated photon flux. This is the photon flux that's actually going to the target. So if you convolute this with the amount of, with the thickness of the target, then this gives you the amount of data, or the rate of interactions that you expect for these different photon energies. So this is just the technique, and you won't have to do this sort of analysis, but what will happen is that, at least to start out with, for this summer, we're going to get data that won't give you necessarily an absolute photon flux, but at least give you the relative photon flux in each bin. So that will make it easier to combine data from different runs, and so it'll be stored in the CCDP, for these different points, and then eventually one will want to get the absolute flux, and that's done by another measurement that I won't go into, but that procedure is still being commissioned. And then one last thing that you'll want to keep into account is the polarization of the photon beam, which I won't go into the details of the whole measurement, but it's measured by another detector that's upstream of this. And you get it from the azimuthal modulation of, again, one of these well-known QED effects. And so this is the sort of information that you want to apply later in the game, not in your JANA processor, but in your root tree. And so this will be, this information is still being determined and being extracted from the data. And so I can't give you an answer on how exactly you'll get to it, but this is another thing that you need to A, keep in mind, and then also B, if you're using it in your analysis, you'll need to know the limitations of these measurements and how to propagate it correctly through to your final answer. So I think I'm running out of time a little bit, so I won't talk too much about systematic uncertainties.
5 minutes.
That's all 5 minutes. Okay.
Give it a shot.
Keep going.
Sure. Okay. So then just to say something briefly about these, because one could sit down and you could talk a full day about systematic uncertainties, right? Is that so the quick thing that you can say about this is that systematic uncertainties, an easy way to say is that they're everything that's not statistical uncertainties, right? There's no mathematically well-defined process for determining these things from your data. So that's why I say it's both an art and a science. I won't go into too many details, but different people do have different opinions to a certain extent about these, and so for the younger people in the audience, I would definitely suggest asking different people about what they think about this and some of their experiences. It's always fun. But you can come up with kind of a simple definition of this, Or you can break it down in more details, right? You know, there are some systematics that you can constrain by doing other measurements with the data. You know, if there's any uncertainties in your event selection or the efficiency determination, you know, if you do some of these studies that we were talking about before, you know, that gives you a way of, you know, really nailing things down. You can have systematics due to model measurements, or, you know, some cuts or other techniques that you're using that have some bias in them. You know, maybe it has something to do with your fit techniques, things like that. Or, you know, you can have systematics from your theoretical models that you're using either to fit the data or to generate your Monte Carlos. So I'm mostly listing these things here just that, you know, when you're analyzing the data and getting your final results, you know, these are all things that you need to take into account and keep in mind. So I'll start with that. So you know, we have a lot of data to analyze, and I've tried to at least, you know, give some general ideas that, you know, it's fine to develop the analysis in simulation, but you need to look at data very, very carefully, and then, you know, let us know if you see anything weird when this happens, right? You know, we have all these meetings, and, you know, it's really going to be important to communicate between people doing the data analyses and the detector experts to improve the results quickly. And then, as I mentioned before, on Friday, I'll talk about some more logistical details on how we do these data analyses. So, any questions?
Maybe you're going to talk about that tomorrow, but yeah. So to compute the flux or lifetime, those quantities.
Yeah.
After we make selections throughout the run, how are we going to keep that? I mean, I think we right now have flux information that's integrated over the run.
Well,
or almost.
Those numbers exist.
Okay.
Yeah. So with the flux numbers, at least. Yeah. So if you think at least integrated over the run, we're thinking of keeping those flux numbers. Right now, they're sitting in text files that people have, but we're going to put those in the CCDB, make it easy for those to access, and that will be kept in bins and stuff like that. For the lifetime, that should be. I'm not sure how that. Yeah, I'm not sure about that.
That should be incorporated into the flux calculation. So once that lifetime is calculated and you have the answer, a typical user shouldn't need to see that anymore.
Right. Yeah, I mean, I think the idea is, you know, to analyze these things, you want to derive it so that at least for analysis, they're kept there. I think that the lifetime is something that, you know, we want to keep in the RCDB or something like that, so that we at least have numbers for experts or people who are going and looking at it in more detail.
In any case, maybe for this run, we expect, or maybe you want to decide we're only going to use these run integrated numbers.
Yeah.
I mean, to some extent, you can throw away runs that, you know, that's an issue, perhaps.
Yeah, I think that's what we want to do to start off with, because certainly you can imagine doing, you know, you could be doing a more detailed analysis where you actually look for the periods where the beam is on or where you have good lifetime, right? And you're throwing out parts of the run that are just bad or look horrible. But we don't, you know, we don't really have the, you know, the analysis workflow or really all the hooks that we need in our software to properly deal with that.
Probably have enough data that we can be selective, right, and just say, okay, runs that we probably could use that have statistics, but let's just not worry about it at this point.
Mm-hmm. Yeah, and so and I think that's, you know, one of the first goals of the analysis of the Spring data is just figuring out which runs are worth actually analyzing. And I think that we're on that path, but there's, you know, more work to do.
All right. Any questions?
Right.
versus next online?
So I'm going to